Hey guys, I know yesterday we were trying to get some work done on that lab, and I know you guys are having some trouble seeing some things, and the chaotic nature of things slowed you down. So what I wanted to do is just kind of walk you through what yesterday's lab was about so you can watch it on here, take your time, use my measurements. Hang on, somebody's at the door. You know, back and doing a video for the lab kids. Stop back in like 20 minutes. I think you both did well, by the way. I think off the cuff you were 81 out of 82, and I think you were 83 out of 82. I think so. But double back, and I can tell you for sure. Oh, sorry about that. Sometimes it's easier not to stop. All right. So the whole idea of what we were doing there was it's all about measuring things, and different instruments have different abilities to measure. And everyone's always like, well, how do I know how well it can measure? And the way that you know is by looking at the markings on whatever the instrument is. So if I go in my drawer here and I take out this graduated cylinder, and if I bring that up so that you can see, right, what you'll see is that there's a bunch of little markings on there. So you've got a line here at 50, and then a line here at 60, and there's 10 marks in between. All right, so what you're looking at is a scenario where each line you know is worth 1, right? So 50, 51, 52, 53. So I know this is 54. I know this is 56. I know this is 58, and so on. So that means I am 100% certain whenever something lands here in my grad cylinder, if I fill it up with a liquid, that it's above 54. But I also know it's below 55. So I am absolutely certain about the 5. I am certain about the 4. Right? But I can still estimate. I know it's in between, so now I'm going to estimate what the next thing is. I think it's leaning toward the 55 more. I'm going to say it's 54.7. And anytime you measure, you always get just one estimated number. So if your device measures in ones, you're accurate to the ones place. Right? And if this were math class, right, you have the tens, the ones, the tenths, and then it'd be the hundreds. Right? Not every instrument measures that well. For instance, if I brought out your centimeter ruler or just a good old-fashioned beaker, get your 100. If I look at this beaker, I see lines every 10. So the beaker goes 20 dash, then there's a line dash 40. So I know it's measuring every 10. So if a liquid in my beaker lands here, I'm certain it's 30. I know it's not 40, which means I'm estimating where I think it is, 37 milliliters, because I'm certain about this and I'm estimating this. And the reason that is this guy measures in tens. So I'm certain about the tens place, but I'm estimating the ones place. Right? So if it measures by tens, I know the tens, I'm measuring the ones. If it measures by ones, I know the ones, I'm measuring the tenths. Right? We have a centimeter ruler, and our centimeter ruler looks like this. There's a 1 down here. It's got 9, which means each one of these guys is worth 0.1. So if it measures in tenths, then I know I'm certain about the tens. I'm certain about the ones. I'm certain about the tenths. I'm estimating the hundredths. Right? So if this guy measures to here, say, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. I know it's no 10s. I know it didn't make it to the 1, no 1s. I know 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. I know it's 0.7, and I know it's past the 0.7, so I can say 0.74. Right, so I can estimate to the hundreds. So as we went through and measured stuff in the back, in the packet that you're seeing, I tried to help you guys out with that and say, hey, this should be 2 passed in your data table, or this should be 1 passed in your data table. But I'll be telling you what those numbers are, so you're not going to get it wrong. I just want you to understand why they are what they are. All right, so let's transport to the back and get you guys some good lab data. All right, and the tasks that we were doing were fairly simple. All right, the first task we were doing was we were trying to figure out what the volume of your the volume of your beaker, your biggest beaker, is supposed to be. So if you look at that procedure, it tells me to measure the inside diameter from inner edge to inner edge. So I went into my drawer. I got my biggest beaker out. I go and I get my centimeter ruler. If you take a look at your centimeter ruler, nice and close, right, you can see that it is measuring in tenths, because here's the 0.1, right, and we have 10 ticks that gets us to 1 centimeter, so it's 0.1, 0.2, 0.3, 0.4. That means this guy can go 2 places past the decimal. So if I bring up my beaker and we measure inner edge to inner edge like this, we're going from the inside edge of the glass to the inside because the liquid only lives in the middle. All right, so I'm going to do that so you guys can see. All right, and if I do that, I would go ahead and say that that value is 9.75. So in your data table, you want to write 9.75 in for the inside diameter of your beaker. All right, so the line that says inside diameter, your top line, that's your 9.75. Right, then what I'm going to do is I'm going to measure the height of this guy. Right, so we go here, and I'm measuring what it is from the bottom to the top if we maxed it out. Right, and we're going to get the height of this guy to be 12.70. So I'm going to say that is 12.70 on the height. That's going into line 2. Why do I need these things? Well, if you look back to the procedure, we can calculate the volume of a cylinder, which is basically what this is, right? A really wide cylinder, by using the equation pi r squared h. Right? So you can do a math problem where you calculate that. Right? And if I do that, now it's a sig fig problem as well. I've got my 9.75 that has 3 sig figs. I've got my 12.70, which had 4 sig figs, right? And we're going to be doing some manipulations there. Now notice the 9.75 was the diameter. I need the radius, which is halfway across this guy, but I can't really measure that into the middle accurately. So what we do is we measure all the way across the 9.75, and then you have to cut that in half for your radius. So you'll take your half of your 9.75 and square it, and then times it by the height of the cylinder, and now you are going to get what your experimental volume of your grad cylinder is. All right, and if you look real close on here, the accepted value, my blue shirt's probably the best, showing it, tells you it's 600 milliliters, and that's why I filled that in. All right, so that was part 1 of the experiment. Right, part 2 wants us to determine the mass of water. Right, so to do this, we're going to use our graduated cylinder. Right, so we take our graduated cylinder, right, and we're going to take that all by itself and put it on the balance. Right, so give me a second. I got to turn on the electricity. All right, if I turn on my balance, and I'm going to put this onto the balance. And hang tight. The number for your empty cylinder mass is 68.25. So on your top line of data table 2, it's 68.25 grams. And that one you don't really estimate because the balance does it for you. You're just reading that number directly off of the balance. All right, so then the next thing we do is I'm supposed to put somewhere between 25 and 30 milliliters of water in this guy. All right, so we're going to do that. Okay. All right, and it's important that I record how much water's in here. All right, so we got to make sure the outside of it is dry because that water that's not in the cylinder isn't going to read on our volume measurement, but it's still going to add to our mass because it's attached to it. So I'm going to make sure it's nice and dry. Okay. All right, and then we're going to zoom in on this. I'll turn so you guys can see numbers. All right, and when you do this, you are going to read from the bottom of the liquid level, and that thing gets a name. It's called the meniscus, where it's lowered out like that. All right, so if we do that, right, and I set it on the counter so the water settles, I will tell you that I didn't quite make it there, right? I'm above the 24, but I'm below the 25. So I'm going to call that 24.8 milliliters. All right, and that goes in your third line down. All right, now I'm going to go get the mass. So 24.8 milliliters is your volume of water. All right, so when I put this guy on the balance, it read 92.97. There's your mass of your cylinder with your water. So you've got your cylinder with your water was the 92.97. And the number I gave you earlier, that was the empty cylinder. Right. So it says for this guy here, use the thermometer to get the temperature of the water. And the reason we need the temperature is we want the density of this guy. And density is temperature dependent. So I go in my drawer and I get out my thermometer. And if I get this close enough that you guys can see, you'll see that the thermometer is like the grad cylinder. It measures in ones, right? Because there's that line there at 10, and there's a line there at 0, and there's 10 ticks in between those two. Right? That means each one is worth 1. Right? If it's worth 1, I know of the ones. What I'm going to do is I'm going to estimate to the tenths, right? To the 10th spot. All right, so if I'm looking at this guy, I know, and I'll see if I can do it on the camera with you. I know he's above 20, and if you look there, he's above 21, he's above 22, he's above 23, all right? He's sitting probably at 23 and a half. So we're going to say 23.5 degrees Celsius for your temperature, okay? And the water should be the same temperature. All right, but just to confirm that, I put it in here and I let it stabilize. Oh, water's a little bit colder, actually. All right, so it dropped. The heat from my hand must have been raising the temp a bit. All right, the number you guys want to use for your temperature is 19.5. All right, so 19.5 degrees Celsius is your temperature. All right, then what they did was they went into our chem book onto page 899. And on page 899, there's a table. And that table tells you the density of water based on temperatures. So what we did is we read down that column to our nearest temp, and 19.5 was near the 20. and we got our density. All right, so your density is going to be 0.99820. So 0.99820 grams per milliliter is what you guys are putting on your density of water line. All right, now, the next three table lines that you see here, mass of water accepted, mass of water experimental, and percent error, they all have little stars next to them. A little star means there should be supporting math work that goes with it. All right, so it tells you how to generate these numbers in the procedure, and just message me if you're struggling with that part. All right, but it's pretty straightforward. All right, now that you have the good numbers, you can just do what it tells you to. When you subtract, watch for places past the decimal. When you multiply and divide, watch for total number of sig figs. All right, into part 3, we want to find the density of some aluminum, this stuff. Let's get you guys a look at the aluminum. Okay. All right, and what we're going to do, all right, is first add 25 to 30 milliliters of water to our grad cylinder, right? And sure enough, we already have that from before. And it says record that in the table. So just to make sure I haven't lost any, that number is still 24.8 milliliters. So it's there. It says using the balance, measure the mass of the cylinder with the water. Put it in your data table. You have it from before, but again, I'm double checking it to be sure. That number is 92.93. Right, so in my data table for the volume, 24.8 milliliters. For the mass of water in the cylinder, 92.93 is that. All right, now it says volume of metal shot in water. And they told us that they want to add metal shot into this until we raise it roughly 10 milliliters. So I'm going to shake some of this aluminum into here. And it just needs to be roughly 10. So it doesn't have to be at all. Okay, so let's say I put, all right, all of that. All right, so you can see I've got the aluminum in here now, and it definitely raised the liquid level inside the container. All right, and what we're doing right now is we're using something called Archimedes' principle. Archimedes' principle was the guy who got in the bathtub to figure out how much volume his body took up. We knew the water by itself. I dumped this solid in here, however much the water goes up by, that is the volume of the aluminum. So I'm going to get you what that total volume is. So if I look at this thing, I'm going to call that 37.0 milliliters. So on your third line down, you're writing 37.0 milliliters because it is right on the 37. So I know it's 37, and I think it's right on it, so I'm estimating that it's the 0.0. All right, and now I'm supposed to get the mass of this guy because now I'll know how heavy the aluminum was. All right, that number is 124.65. All right, so the mass of this whole combined thing is 124.65. All right, now, if you notice, the rest of the table has stars, which means I'm not measuring anything else, right, in the lab. These are all calculations. The volume of the metal shot, here's the high water mark. I knew what it was before. That's going to be a subtraction. The mass of the metal shot, I knew how heavy it was with it in there. I knew how heavy it was without it in there. That's going to be a subtraction. The density of the metal, you have the mass, you have the volume. That's a D equals M over V problem. Right? The accepted density of aluminum, I put in the table for you. It says it's 2.7 down there on the bottom. Right? And then, as always, you can calculate your percent error once you have the accepted and the experimental using the equation A minus E over A times 100. All right, so hopefully that helps you guys understand what was going on in the lab a little bit better. And if you have any questions on the math or how to set things up, feel free to reach out. We can meet virtually, or I can just shoot you an email. The one thing I will say is when you're doing your star calculations, the math work that gets you those numbers, show all your work, Every number should carry a label. So don't write a single number that doesn't have a label on it. All right, and then just box those final answers. Once you get that stuff done, right, that is basically the lab report. You'll do a title, you'll do a purpose, and this can be handwritten. Okay. Your procedures in here, don't worry about it. Materials are in here, don't worry about it. The data tables, I'll need those. All right, so send me a picture so I can see what yours were. Right, and then I need the big one, the picture of your star calculation, so I can see that you're doing your math right. And then just like every lab, the 5-part conclusion where you answer those 5 questions. I hope everything else is going well. I will see you guys on Monday. If you're going to homecoming, have fun, be smart, be safe, and I'll talk to you guys soon. See ya.